Okay, good morning. In today's session, I will be discussing about some examples on shear force and bending moment diagrams for simply supported beam under various loading conditions. So, what is shear force? Shear force is in beams we have transverse loads acting perpendicular to the axis of the member. So, the cross section of the beam, whatever shape it may be, it will be subjected to tangential forces. The cross section at any point is subjected to transverse loads, the tangential loads, which is called as shear force. And at any section, the shear force is given as algebraic sum of all the forces acting either to the right of the section or to the left of the section. The shear force at any section X is given as the algebraic sum of all the forces acting either to the right of it or to the left of it. Okay, and the convention for shear force, sign convention for shear force is left side upwards, left side of the section upward force is, for example, here the reaction at A is upwards and that is positive. The load W1, W2, etc. are downwards, which are to the left of the section. So left of the section downwards is negative and left of the section upwards is positive. Similarly, right of the section downwards is positive and right of the section upwards is negative. For example, the load W3 here is to the right and acting downwards, so it is positive. Right side downwards is positive and right side upwards is negative. Okay, so we follow this sign convention for shear force. And also for bending moment, bending moment is at any section all the sections are subjected to bending moment. In beams, each and every section is subjected to bending moment. For example, you consider this for some sort of loading. So at any section, bending moment is moment of all the forces, algebraic sum of the moments of all the forces acting either to the left or to the right. So we consider either forces acting to the left of it or to the right of the section. Okay. So the moments of all the forces acting either to the left or to the right. Understand? And how about the sign convention here? The moment of force which produces sagging in the beam are positive. For example, here VA produces sagging, this displacement. So the moment due to VA is positive, and the load W1 and UDL, they produce hogging, downward bending, something like this. So the moments due to these forces are negative. So sagging moments are positive and hogging moments are negative. So when you consider right side, VB produces sagging and W2 produces hogging. So moment due to VB is positive and moment due to W is negative. So this sign convention we follow for bending moment in beams. So with this introduction, let us discuss some examples how to draw the shear force and bending moment diagrams for different load conditions. in case of simply supported beams. Let us consider the beam shown in figure. Uh, the beam AB is of span 10 meters and acted upon by two point loads. One 20 kilonewtons acting at C, and the second one 40 kilonewtons acting at D, and a UDL of 30 kilonewton per meter acting over BD, acting over the right half of the span BD. Understand? So for this load condition, how to draw the shear force and bending moment diagrams? Okay. So as a first step, what we do, we find the support reactions, say RA and RB. For this, we consider the equilibrium conditions sigma m A equal to 0. So considering the moments about A of all the forces, okay, we get the reaction RB. So RB into 10, this is anti-clockwise. Okay, this meaning of this equation is sum of anti-clockwise moments is equal to sum of clockwise moments. That is the equilibrium condition. Or algebraic sum of the moments is 0. We can say like that also. Okay. So here anti-clockwise moment is due to RB and clockwise moments are due to applied loads. Okay. So the sum of these moments 20 into 2 plus 40 into 5 plus UDL moment is 30 into 5, the total UDL into its distance from A. So 5 plus 2.5. This is the point of application of UDL, 7.5 meters. So 7.5. So this gives RB 40 plus 200, 240 plus 150 into 7.5, 150 into 7.5. So this comes out to be 75, 750 plus 375. So 1125 plus 240. So it comes out to be 150 into 7.5 plus 240. So 1365 divided by 10. So it is 136.5 kilonewtons RB. With this, we find RA as 60 plus 20 plus 40, 60 plus 30 into 5, 150, 150 minus RB, 136, 136.5. So this gives RA as 73.5 kilonewtons. Okay, RA is 73.5 and RB is 136.5. So knowing the reactions now, we can draw the shear force and bending moment diagrams. For that, again, we consider this 30 kilonewton per meter and 40 kilonewtons acting at D and 20 kilonewtons acting at C. 2 meters, this is 3 meters and this is 5 meters. Now RA is 73.5 and 136.5. So to draw the shear force diagram or bending moment diagram, what we have to do is we consider various sections, okay, in portions AC, CD and DB. So why we need to consider so many sections? Because when you find the shear force at section X, that equation for shear force is valid from A to C only, because at C there is a load acting. Okay, so when it crosses the section C, when the section crosses C, then the equation changes. Equation for shear force or bending moment changes. That means the equation for bending moment in portion AC is not valid for bending moment in portion CD. So when you consider the section in portion CD, the load 20 kilonewtons comes into picture. Okay, so we need to consider different sections in different portions. Wherever there is a change in loading, we need to consider a separate section. Okay, and the origin for this can be taken either to the left side or to the right side, it doesn't matter. Okay, for any section you can consider the origin, that is distance x, either from A or from B, it doesn't matter. Okay, so for section between AC we take origin at A, for section between CD we take origin at A again, but for section between BD we take origin at B. Okay, we take origin at B. So here for section between AC, this x varies from 0 to 2, that is from A to C, 2 meters. Similarly, for the section between CD, this x varies from 2 to 5, that is from C to D. X origin we are taking at A, that means when the section is at C, x is 2. When the section is at D, x is 5. Okay, so the limits for this x are 0 to 2 to 5. The limits for this x are 0 to 2. And how about this section between BD? X varies from 0 to 5. That means B to D. It is clear. So like that, we have to consider the limits for x. Now let us consider section between AC first. Section between A and C. Portion AC we consider. So what is the shear force at this section? Shear force at any section is algebraic sum of the forces acting either to the left side or to the right side. That's what is we have defined it as. Okay, so shear force at x, considering left hand side, we are considering origin at A, so we are considering left side of the section. The forces acting to the left are the reaction RA only, so that is upwards. So left side upwards is positive. So the shear force at A is 73.5 kilonewtons. It is positive because the convention that we follow is left side upwards is positive. So when you observe this, it is independent of distance x. What does this mean? Shear force remains constant between A and C because there is no load acting between A and C. Okay, so this can be concluded where we in whichever portion there is no load acting, the shear force remains constant between the ends of the section. Okay, similarly between C and D also there is no force acting. Force is there at C and at D, but there is no force in between C and D. So the shear force remains constant between C and D. That means constant means it will be a line parallel to the axis. Okay, when you plot the diagram, the shear force line is parallel to the axis of the beam. It is clear. But in case of portion BD, there is UDL acting. So shear force will not be constant and it will be varying linearly from one end to the other end. Okay. So What does this mean now? At x equal to 0, the limits of x are 0 to 2. Okay. So at x0, shear force at A will be 0. X0 means section is at A. So shear force at A is, it is 73.5. It is independent of distance x. Similarly, at x equal to 2, the section will be at C, and shear force at C is also 73.5 kilo. Both are positive only. Okay. Similarly, bending moment at x. Bending moment at x. Shear force at x is independent of distance, but bending moment at x. What is the bending moment at x? Considering left hand side in portion AC, it is the algebraic sum of the moments of all the forces. Algebraic sum with the sign convention, sagging positive and hogging negative. With this convention, we add the moments. Okay. So 73.5, the reaction at A is only the force acting to the left. So the moment due to this force is positive because it produces sagging moment. Okay. So the moment due to reaction is 73.5 into x, and the limits for x in portion AC are 0 to 2. Okay. So when x is 0, that means the section will be at A and bending moment at A will be 0. Bending moment at A will be 0. Similarly, when x is equal to 2, bending moment at C, because the section will be at C, so bending moment at C will be 73.5 into 2. That is 147 units are kilonewton meters. Kilonewton meters. Okay. So bending moment at A and bending moment at C we have found. Okay. Similarly, considering section between CD, considering section between CD, the limits for x will be 2 to 5, considering left hand side, considering left hand side of the section. Origin at A again, the limits for x will be from 2 to 5. So shear force at x, shear force at x, considering left hand side, 73.5 upward, that is positive, and 20 downward, negative. So 53.5 kilonewtons. Okay. And it is also independent of x. If you observe, shear force between CD is also independent of x. Okay. It means it remains constant from one end to the other end, from C to D. Therefore, shear force at C equal to shear force at D equal to 53.5 kilonewton. Okay. It is clear. Similarly, bending moment. What is the bending moment at x at this section now between CD? Considering left hand side, the forces acting are the reaction RA 73.5 and 20 kilonewtons load at C. These are the two reactions acting which produce bending moment at C, at the section X. Okay. So bending moment due to 73.5 kilonewtons is 73.5 into its distance x. It is sagging positive minus 20 into its distance. 20 into this distance. What is this distance? X minus 2. X minus 2. 20 into x minus 2. Okay. So here the limits for x are now 2 to 5. Okay. That means at x equal to 2, bending moment at C will be, when x is 2, this term becomes 0, second term becomes 0, you will have bending moment 147, 73.5 into 2, 147 kilonewton meters. This is same as bending moment at C considering section AC. Okay, you will get the same value. Next, bending moment at D is, that is when the section is at D, x is 5 meters now. When x is 5, section will be at D. And what is the bending moment now? 73.5 into 5 minus 20 into 5 minus 2, 3. So this comes out to be 307.5. 307.5 kilonewton meters. Okay, it is positive again. Okay, so next, like this, we have to consider sections, various sections, and we find shear force and bending moment at salient points. Okay, now let us consider the section between BD. Section between BD. For this section, considering right hand side now, the the shear force at x is now considering right hand side. So you have the reaction VB upwards, RB upwards 136.5. So right side upwards means negative. The convention for shear force, left up is positive and right down is positive. Okay, atlage right down, left down and right up are negative. So right side upwards is negative. And the load UDL is acting to the left. So what is the UDL? 30 into x. So the shear force at x, considering portion BD, the limits for x are from 0 to 5. The limits for x are from 0 to 5. So shear force at x is minus 136.5 plus 30 into x. Okay, plus 30 into x, considering right hand side. So total UDL acting to the right of the section is 30 into x length. Okay. So now at x equal to 0, shear force at B you will get. That means the section will be at B. So what is the shear force at B considering x0? x0 means this term is 0. So you will have shear force at B as 136.5 negative. Negative as per our convention. Okay, because it is upwards to the right of the section. Similarly, shear force at D. Shear force at D. That means when x equal to 5. So minus 136.5 plus 30 into 5. X is equal to 5. So it becomes plus 13.5 kilonewton. Plus 13.5 kilonewtons. So the shear force is varying from B to D. Okay, at B it is minus 136.5, at C it is, at D it is plus 13.5. So it is varying linearly from minus 136.5 at B to plus 13.5 kilonewtons at D. What does that mean? In between it is changing sign. Okay, it becomes 0. The shear force becomes 0 in between B and D at some point. Okay, and that point where the shear force becomes 0 is obtained by equating this shear force to 0. So by equating shear force at x to 0, that is minus 136.5 plus 30x to 0, you will get x as 136.5 by 30. Okay, so it becomes 4.55 meters. So at x equal to 4.55 meters from B, the shear force is 0. Okay, at x equal to 4.55 meters from B, the shear force is 0. So why do we need to find this distance is because we know that at the section where the shear force changes sign, the bending moment will be maximum. Okay, bending moment will be maximum at this section. Okay, so to find bending moment at this section, we need the distance. Okay, maximum bending moment, we need this distance. So for that reason, we find the distance where the shear force changes sign. Okay, similarly, you consider bending moment now. Bending moment at x for section between BD, bending moment at x. So what is the bending moment at x? You have 136.5 x, that is reaction at B producing positive bending moment sagging minus 30x UDL into distance of centroid x by 2. So it is 136.5 x minus 15x square. So this is the equation for bending moment at x. Okay. Now in this equation, now the limits for x 0 to 5. So at 0, bending moment at B you will get, which is 0. That is when x is 0, bending moment will be 0. That means bending moment at B is 0. Similarly, bending moment at D, that means when the section is at D, that is at x equal to 5, the bending moment is 136.5 into 5 minus 15 into 5 square. Okay, this comes out to be 307.5 kilonewton meters, because this will be same as this bending moment. Okay, yeah, considering CD we have calculated bending moment at D, and considering BD we calculated bending moment at D. These two must be same. Okay, so you're getting bending moment at D as 307.5. Now what is the variation here of bending moment? If you observe this equation, it is clear that it is parabolic variation. The bending moment variation is parabolic, and whereas the shear force variation is linear. Shear force varies linearly and bending moment varies parabolically between B and D. Okay, so when UDL is acting, shear force varies linearly and bending moment varies parabolically in the region where the UDL is acting. Okay, now we need to find maximum bending moment. What is the maximum bending moment? Between B and D at one point, you will have bending moment maximum. And what is that point? That is at x equal to 4.55, where the shear force changes sign. So substitute this 4.5 in this equation of bending moment. That is 136.5 into 4.55 minus 15 into 4.55 square. And this comes out to be 310.54 kilonewton meters. Okay, at D it is 307, and at the point where the shear force changes sign, it is 310.54. This is greater than this. Okay, so 310.5. Now let us plot these diagrams, shear force and bending moment diagrams. We have calculated these values at each and every point, salient points. So we can now plot these diagrams. Okay, let us now plot the bending moment and shear force diagrams. To draw the shear force diagram, first let us draw the loading diagram. loading diagram as given, you better plot the shear force and bending moment diagrams in line with the loading diagram so that you can understand easily how the shear force or bending moment varies with the loading. Okay, 30 kilonewton per meter. So now to draw the shear force diagram, this reaction is 73.5 kilonewtons and this is 136.5 kilonewtons. Okay, so shear force at A is 73.5, which is same between A and C. So shear force at C is also same. That means this line remains parallel to this baseline. Okay, x-axis. At C, the shear force between CD, when you consider the shear force at C is, that means just to the right of the section, just to the right of C, the shear force is 73.5 minus 20. And just to the left of the section, the shear force is 73.5. Considering left hand side, the shear force at C just to the left is 73.5 and just to the right it is 53.5. And there is a drop in the value of shear force by 20 kilonewtons. Okay, that means at the point where the concentrated load is acting, there will be a drop or rise in the value of shear force. Okay, so there is a drop of shear force by 20 kilonewtons. Drop in the value of shear force by 20 kilonewtons when you move from left to right. When you move from right to left, there will be a rise in the value from 53 to 73. When you move from left to right, there is a drop from 73 to 53. Okay, that is by 20 kilonewtons by the magnitude of the point load. There will be a sudden drop change in the value of shear force by a value equal to the magnitude of the force. Okay, similarly from C to D, the shear force remains same 53.5, but at D there is a point load acting, so there will be a drop in the value again by 40. So shear force becomes 53.5 minus 40, that is 13.5. Okay, this we have already calculated all these values, just we plot them. So even without calculating also you can plot the bending moment shear force diagram, but not bending moment diagram. Shear force diagram can directly be plotted without working out all those. Okay, just by finding reactions we can calculate, we can draw the diagram. Okay, now between D and B, the shear force varies from plus 13.5 to minus 136.5. Okay, so that variation is linear. This variation is linear. Okay, it is clear. So this is a straight line. Linear variation means it is a straight line. This will be a straight line. Okay, and at some point E, the shear force is changing sign, and the distance of this point from B is found to be 4.55. Okay, just we have calculated just now. It is 4.55 meters from B, and at that point E, the bending moment will be maximum. At that point E, the bending moment will be maximum. Okay, so what is the the distance is okay. This is negative and this is positive. The negative values will take below the line, baseline, and positive values above the baseline. This is the baseline. Okay, it is clear. Now, the bending moment diagram. Coming to bending moment diagram, the bending moment at A is 0 and bending moment at B is also 0, and bending moment from A to C 0 to 147, 0 to 147, and at D bending moment is 307. At D the bending moment is 307. Okay, now this is D. At E, that is at 4.55 meters from B, bending moment is maximum and that value is 310.5. Okay, and the variation of bending moment from D to B is parabolic. Okay, this is parabola and this is straight line. Shear force variation is straight line and bending moment variation is parabolic. Okay, so here if you observe, the bending moment is positive throughout the beam. So in simply supported beams, okay, in simply supported beams, the bending moment will be positive for all the load cases except when a couple is acting. Except when a couple is acting. When a couple is acting, there is a possibility of negative bending moment also, but it depends on the magnitude of the couple also. Okay, but for all the other load cases in simply supported beam, the beam always sags. That means the bending moment will always be positive between the ends of the beam. Okay, for simply supported beam for all the load cases except when a couple is a concentrated moment actually. Two equal and opposite forces separated by a small distance, they constitute a couple. Okay, yeah, in such case there is a possibility of negative bending moment in some portion of the beam, but for all the other load cases the bending moment will always be positive in case of simply supported beam. Understand? So these are the shear force and bending moment diagrams for the given beam. Okay, let us now consider second example. Second example. Second example is similar to the previous example only. Similar to the previous one. The difference is instead of point load at D of 40 kilonewtons, there is a couple acting at D. There is an anti-clockwise couple acting at D of magnitude 40 kilonewton meters. 40 kilonewton meters. Okay. So, how to work out this problem? How to draw the shear force and bending moment diagrams for this? The procedure is same as before. First step is to calculate the reactions RA and RB. Okay. So in this case, you will get RA equal to 57.5 kilonewton and RB equal to 112.5 kilonewtons. Okay. How will you get these reactions? By considering equilibrium equation sigma m b equal to 0. Okay, and sigma MA equal to 0 or sigma V equal to 0. Sum of vertical forces is equal to 0. Algebraic sum. Okay. So after finding the reactions only, we can proceed to find the shear forces or bending moments. So the very first step is to calculate the support reactions. Okay. Before proceeding to find the shear force and bending moment at various sections, first we have to find the support reactions. Okay. In any beam, we need to first find the support reactions. Understand? So here also, by considering various sections between A and C, one section, between C and D, one section, and between B and D, one section. For this, we take origin at B. For this, we take origin at A. And for this section, we take again origin at A only. Okay? Yeah. Let us continue this later. Now let us conclude.
Like, share and subscribe. Hit the bell icon for more updates.